Alright, so good afternoon students. Today we will talk about the correspondence between quantum statistical mechanics and the classical statistical mechanics in the limit of high temperatures and low densities. This is the last subject of our discussion, and an important discussion in the sense that it tells you how to seamlessly connect the quantum world with the classical world. And of course, the only way to connect is when you start from quantum mechanics, you can take this high temperature low density limit and go to classical mechanics. You can't do it vice versa, because quantum mechanics was constructed when classical mechanics failed to describe certain experimental phenomena. So, it was a theory that was set up with certain principles and certain rules, axiomatic rules, and this makes this correspondence unidirectional, in the sense that there is no way you can start with a classical calculation and show by some limit that quantum effects arise. That is impossible. You can only start from quantum mechanics and take a classical limit and show classical results. And I will explain this by starting with our quantum statistics for both Fermi systems and Bose systems, and take the high temperature low density limit, especially when the system is very large, because this is where a natural classical to quantum correspondence occurs. Okay. So today I am going to talk about correspondence between quantum statistics and classical statistics, or it can also be called as quantum to classical correspondence, or classical statistics as a limit of quantum statistics, whichever way you want to call it. Now, I would like to start from a recollection that we have made in the context of partition functions of real particles. So, if you recall, we had constructed the grand canonical partition function. Okay. So, I am writing down the logarithm of the grand canonical partition function. You can consult your notes for this particular expression. It was given as this expression where we summed over all possible energy states. Okay. The plus minus sign here corresponds to the case where the system of particles is a fermionic system or a bosonic system. Okay. So, this is basically summation over all energy levels ln of 1 plus or minus e raised to beta mu minus E j, where the plus is for the Fermi statistics and the negative is for Bose statistics. Okay. Let us label this equation as 1. If you do not recall this, then it is not a problem, because you can derive this expression very quickly. If you want to derive it from first principles, then you should know that a correct enumeration of states or enumeration of the partition function is very difficult if you want to do this in canonical ensemble, that is the ensemble of fixed n, v and t. And then we said that this enumeration of states becomes very simple if you allow the number of particles in the system to fluctuate, meaning that you do the calculation in grand canonical ensemble, which is the ensemble of constant chemical potential, volume and temperature. And then we had shown that the restricted sum becomes easier to compute because you allow n, the total number of particles, to fluctuate from 0 to infinity, thereby taking each term in the summation independently, and you can construct this expression 1 very easily. This was the subject matter of last lecture. I am just bringing it up as a recap. Anyway, we will note our last lecture's outcome, which is the equation 1, our grand canonical partition function, and proceed from here. Now, how do we take classical limit? Classical limit is the limit, as I keep saying, is the limit of high temperature and low density, meaning if you take the number density, now this has the dimensions of 1 upon length cube. I want to construct a dimensionless number. So, which means I must multiply it by cube of some length. Now, this is a dimensionless number. Okay. So, this dimensionless number, if it is much smaller than 1, then I am in the classical limit. Okay. Now, how can I reach this? See, either I can take n to be very small, meaning I have blown the volume to be very large, such that my density has become very small, and this de Broglie wavelength here, the de Broglie thermal wavelength, has to be very small. So, if both n and lambda become very small and lambda cube is much smaller, then the product of these two small numbers will definitely be much smaller than 1. I know that de Broglie wavelength is given as some h over square root of 2 m 2 pi m k t. So, it is not difficult to see why at high temperatures I will get a classical limit. So, if my temperature is very large, the de Broglie wavelength will basically be much smaller. It will go as 1 upon square root t. So, at high temperatures the de Broglie wavelength is much smaller. So, lambda cube becomes even smaller, and I have also taken volume to be large or density to be less. So, high density low high temperature I am sorry, low density and high temperature limit naturally corresponds to the classical limit. So, you can reach the classical limit by low density and high temperature. Okay. The quantum limit is naturally the limit where we are doing our calculations, and this is the limit where we expect n lambda cube to be much larger than 1, and this limit can be reached by taking high density and low temperatures. Okay. So, this is like saying that at any temperature I can see quantum effects if I go and increase my density. Similarly, at any temperature I can see classical effects if I keep my density sufficiently lower. Okay. So, you can take the classical limit here, which is the subject matter of our interest, and show that the partition function reduces to our well known canonical partition function. So, using classical limit, or I would say applying classical limit, okay, which is basically the limit n lambda cube being much smaller than 1, we will basically show that our grand canonical partition function reduces to our familiar partition function for an ideal gas. ideal gas, which is, if you recall, it is nothing but volume to the power n over, let me use a different color here. If you remember the expression, it is volume to the power n over n factorial divided by h to the power 3 n to 2 pi m over beta raised to 3 n by 2. This is our canonical partition function. Okay. So, I am going to derive this from our quantum partition function in the classical limit. And in doing so, we will discover that the correct enumeration states, which is this n factorial here, which avoids overcounting the microstates and hence gives you the correct definition of entropy, is naturally embedded in your calculation. Also the cell factor H also appears as a remnant of this quantum to classical correspondence. So, both these factors which were sort of substituted in an ad hoc fashion in classical mechanics are no longer substituted as ad hoc, they are embedded in the calculation. And now you know why this H was called as Planck's constant, because here H is Planck's constant and its high temperature low density limit reduces to a classical partition function, where you had taken an H keeping just the notion that I want to keep Z dimensionless and I want to have some sort of a scale of the phase space. So, I have taken an H which has a dimensions equal to action, angular momentum, is now realized as the Planck's constant. So, we will now say that H is Planck's constant. We could not have said Planck's constant earlier, because this was a calculation done by Boltzmann and Gibbs, which predates all quantum mechanical work. Okay. Okay, so let us proceed from here. So, I am going to basically write down the occupation number or basically the average occupation number. So, this is nothing but the ensemble average value of particles in some jth quantum level, and we know that this is nothing but 1 over e raised to beta E j minus mu plus or minus 1, where again these two signs correspond to whether the statistics is Fermi-Dirac or Bose-Einstein. Okay. Now, we are taking a high temperature limit, which means I am going to take in fact we are going to take both high temperature low density limit, which is a classical limit. So, under high T and low density, I can safely say that most energy levels are unoccupied, and the reason is the following. At low density, I have high volume, okay, which means that the spacing between the energy levels will be almost negligible. These discrete states form a continuum now, right, because your energy levels are proportional to 1 upon L square, okay, h cut square k square upon 2m. Now, k itself is 2n pi by L. So, k square is 1 upon L square. So, if you calculate the difference between energy levels, it will go as 1 upon L square or 1 upon L, not 1 upon L square, 1 upon, it will go as 1 upon L. So, you can think of the manifestation of large volume as the energy levels forming a continuum. Okay. So, now you have energy levels that are basically forming a continuum, and there are large number of them, there are infinite number of them, and now your temperatures are also very high. So, there is no in principle the particles can be anywhere, and you have a large number of energy levels, which essentially gives you a picture that the average occupation number for any level would be a small number, because most levels are now empty. It is like you have one level here, another level here, and the third level here. You had some particles here, and then you had some particles here. Now, as I increase the volume of the system, I get more and more energy levels in between. Eventually, what happens is, as these particles can, at the expense of very little energy difference, and hop from one level to the other. Okay. So, you will now get a picture which is more or less like this. Because the number of levels are now very large number, they are very close to each other, and because the temperature is very high, these particles can practically go and sit at any level, and there are infinite number of these levels with the separation between them almost negligible. You would expect that the average occupancy number would be a very small number. Okay. So, a consequence of high temperature and low density is that most states become empty. This is the consequence. Suppose you had only low density, but temperature was not high. So, you would have the right hand side picture where the states are very close. Okay. But since you kept the temperature low, most particles would go and sit at the lowest possible states. So, they would be more occupied. Then I cannot say that most states are empty, because the lower levels are now occupied. The fact that you made a large number of them closely stacked and you made the temperature very high, which means now you are making most levels unoccupied. They will all go and sit at levels in such a way that you have only one particle per level at max on an average. So, you can see that I have a large number of states now on the right hand side, okay, which are unoccupied. Okay. In the previous figure, you can see that I can at low temperatures I can at least see most particles and I would say high density. So, because I have taken high density, the energy levels are not forming a continuum, the volume is low. Okay. So, you can say that, and the temperature is also low. So, most particles are taking the lower states. But as I go to low density and high temperature, I have a continuum of states, and I give these particles a liberty to go and sit anywhere in this continuum. As a consequence of that, most states are now unoccupied, which means that my average occupation number is which is given as 1 upon e to the power beta E j minus mu plus or minus 1 is much smaller than 1, okay, as a consequence of this, right. Now, what this means is that the denominator should be dominating. For this fraction to be much less than 1, my denominator should be dominating. So, I can say that e to the power beta E j minus mu plus or minus 1 should be much larger than 1. okay, that is my denominator, which only means that e to the power beta E j minus mu is much larger than 1, because I can ignore 1 is a fixed number. Okay. So, x plus 1 is much larger than 1 means x is much larger than 1. Okay. Now, you can see that two things are here. One is that, let me first split it up. So, I will write it as you can see the left hand side of the inequality is j dependent, the right hand side of the inequality is j independent, which only means that this energy level does not matter, okay. It is arbitrary. Any energy level will suffice or will satisfy this inequality, which can only mean that our minus beta mu is something which is much larger than 1. This is possible because this is actually true, because at very low beta or high temperature, I know that my chemical potential is negative, highly negative. So, minus beta mu has to be a number which is much larger than 1. If you recall your diagram or behavior of chemical potential mu over mu f versus T over T f, you know that it somewhere starts from 1, T equal to 0, mu is mu f, and it crosses 0. So, this is the 0 point, and then it takes a nosedive. So, at larger and larger temperatures, the chemical potential is more and more negative. So, minus beta mu, as beta goes to 0 or temperature goes to infinity, has to be a number which is much larger than 1. Okay. So, I am going to write down beta low or T high, whichever is convenient to you. Okay. So, this is our classical limit, that minus beta mu is much larger than 1. Of course, we have taken the liberty to assume that the system is in thermodynamic limit. Of course, that is not a bad assumption, because most systems that we deal with in laboratory are already in the thermodynamic limit. So, with large number of particles and large volume, the energy levels are very closely stacked. The classical limit just adds one more feature, that I give every particle the liberty to go and sit anywhere. So, in the continuum, if I tell anybody to sit anywhere, I can expect that most levels are unoccupied, right. If I do not give that liberty, I will see that most of them are sitting at the lowest levels. Now, I can't say that Nj is much larger, much smaller than 1 for any j. Okay. Certainly, for lower j's, Nj is not insignificant, but at high temperature, when I have given the liberty to go and sit anywhere in this infinite continuum of states, I can assume to a very good extent that average occupation number for any level would be much smaller than 1. Okay. So, this is the meaning of the classical limit in the large systems. So, now we can proceed from here and note that the total number of particles, which is finite, okay, we only increase the volume to sort of make a continuum of energy states. Okay. And this is given as a summation over all the states with the average occupation number of each state. Okay. And the average occupation number of each state has already been approximated. So, I will say this is approximated to, you can look at the expression here, because the exponent in the denominator is much larger. I can write down this as just I can ignore the plus minus sign, so which basically means that now it does not matter whether you have Fermi systems or if you are dealing with a fermionic system or a Bose system. In the high temperature low density limit, both the Fermi-Dirac and Bose-Einstein systems, or both the boson system and the fermion systems behave identically. So, I am going to write it as just 1 upon beta E j minus mu. Okay. The nearly equality sign should remind you that we are looking at the high T, low density or classical limit. We have taken the classical limit of Bose-Einstein and Fermi-Dirac statistics. Okay. So, this can be simply written as summation over e to the power minus beta E j minus mu. Okay. So, I can clearly take a couple of things outside here. So, I can say that this is e to the power beta mu into summation j e raised to minus beta E j, because this is a prefactor that does not depend on the index j. Okay. And write down for e raised to beta mu as n over summation j e raised to minus beta E j. Okay. Also implying that I can take so I can also take a log on both sides, and this will give me natural log okay. So, let us call this as some equation. We have labeled that as equation 1. So, I am going to label this as maybe equation 2. So, equation 2 has two avatars, one is the left hand side, which is basically this, the other is this, both are the same equations. Now, we can write down in some sense the partition function. So, if you recall your results from classical statistical mechanics. So, we had a relationship between statistical mechanics and thermodynamics, essentially the bridge that we constructed for every problem, and this result was that the logarithm of the canonical partition function was related to the free energy by this expression. Okay. And I am going to write down this as minus beta, and the free energy is the Helmholtz free energy. So, this is just internal energy minus Ts. Okay. Since our goal is to derive classical statistical mechanics from quantum statistical mechanics under this high temperature low density limit, it is sufficient that I derive the classical partition function starting from the quantum partition function, because partition function is the bridge that connects thermodynamics to statistical mechanics. So, if I show that the quantum partition function reduces to the classical partition function, I would have done my job, because from there I can derive all properties of my gas, entropy, pressure, so on and so forth. So, the task simply reduces now to start from the quantum partition function, which is the grand canonical partition function, that is nothing but I know the grand canonical partition function's logarithm gives me an energy scale which is the grand potential, and that is equal to E minus Ts minus mu n. Okay. I know this, but here is the thing, I know that beta times E minus Ts is also equal to ln of canonical partition function. Okay. So, I am going to write this as minus beta times, so or I can just substitute the expression from there. So, this is the fun part. So, I can write it as ln of the canonical partition function plus beta times mu n. Okay. So, now you can see that I can write down, I can just rearrange the terms and write down for the canonical partition function as right, and now we just substitute for these quantities. Okay. So, we are just going to substitute for these quantities. So, first I am going to write down for ln of the grand canonical partition function, which is nothing but my equation 1. Okay. So, go back to equation 1, which is all the way here, okay, and substitute this, the second factor, which is minus beta mu n. Okay. Fine. So, basically what I have done is I have I have substituted for this term with this, and I have written this term as is. Okay. Fine. Since we are in the classical limit, we are interested in the classical limit, I can already assume that my beta times mu or minus beta mu should be a number which is much larger than 1. Okay. So, I can safely put the exponent here to be a very small number, okay, turns out to be very small. Okay. So, then I can write down my right hand side. So, I will say that since minus beta mu is much greater than 1, which is basically the classical limit, just to remind that we are in the classical, we are interested in taking the classical limit, e to the power beta times mu minus Ej is a number which is much smaller than 1. Okay. Therefore, I can use the expansion, since I can write down this ln of 1 plus minus e raised to beta mu minus Ej as simply, I can write it as plus minus e to the power beta into mu minus Ej roughly, and I can definitely ignore terms of the order beta times E I can drop these terms. Well, this is nothing but if I have to show it explicitly, it is nothing but if I have ln of 1 plus x, where x is very small, much smaller than 1, then I can approximate this as x minus x square by 2 plus terms of the order x to the power 4 and so on. Sorry. Right. Now, definitely if I have a minus x here, then I have to say this is plus or minus x, because the even powers of x do not suffer any sign change whether x is replaced with minus x, but all the odd powers will suffer a sign change. So, I can say that to linear order, if x is very small, I can approximate ln of 1 plus or minus x as simply plus or minus x, and I will say that I am not interested in terms quadratic and above. Okay. Fine. So, that is what I have done. So, I have replaced the ln of 1 plus or minus e raised to beta mu minus e j as simply plus or minus e raised to beta times mu minus e j. With that, my right hand side becomes much simpler. There is a plus or minus sign outside, and each term in this summation is coming with a plus minus sign, which means I can now forget the plus minus sign, because if it is plus outside, it is plus inside, it is minus outside, it is minus inside. In either case I get plus only. So, this is a very promising scenario. So, I am going to write down as the left hand side as ln of my canonical partition function, which is nearly equal to summation over j, each term was a ln of 1 plus minus x, which is giving me plus or minus x only. So, I am just going to write down ln of 1 plus x as e raised to beta mu minus e j, and that is it. That is the first term on the right hand side. I have got one more guy that I have to take care of, which is minus beta times mu n. Now, we make simple substitutions, very easy ones. Okay. But before that, let us give this equation a name. Let us call this as equation 3. All right. So, now you have to make very simple substitutions. We will use this one substitution we will use as it is from here, from equation 2. So, we are going to substitute for beta mu as this term. So, I am going to substitute this entire expression for beta mu. Is that okay? Okay. This entire thing is for beta mu. Let us do that. So, I am going to write down the first term as it is. In fact, why do not we substitute okay. So, maybe we can do it in 2 steps, it is better that way. So, from the first term, what I am going to do is basically take okay, let us write the first term as it is. So, it is just e raised to beta mu minus e j, and I said that I am going to substitute for beta mu. Okay. So, I am writing minus n, and for beta mu I am going to substitute what I had written, this term. Okay. Fine. Now, let us try and do something with this term. What can we substitute for this? Again, let us go back upstairs. So, if you look here, this place. So, you can see that this is e to the power beta mu minus e j. Okay. and you have the same thing here, c raised to beta mu minus E j, we just roll out a minus sign, and this is nothing but n. Okay. So, we will substitute with n, and you can refer upstairs. Okay. So, now let us write down the right hand side. So, this becomes n minus n ln n, this is already looking like something, plus n ln summation j e to the power minus beta E j. N minus n ln n looks like a familiar approximation. This is a Stirling approximation of minus n factorial. Okay. So, this is the Stirling approximation of minus ln n factorial. Okay. Plus the second term I am simply going to write down as ln of summation j e to the power minus beta E j to the power n. Okay. This is because you know it is simply if I have n times ln of x, this is nothing but ln of x to the power n. Okay. So, this is what I have done to the second term, I have taken n as an exponent because I want to combine all the logarithms. So, I can now combine my right hand side because both of them are log a plus log b is log of a times b. So, I can use this since I have a negative sign here. So, I am going to take log a minus log b is nothing but log of a over b. Okay. So, I can write this as a natural log of summation e raised to minus beta E j the whole to the power n divided by n factorial. What is on the left hand side? The logarithm of the canonical partition function. So, I know my canonical partition function now. I can simply take antilog on both sides and that will give me an expression for the canonical partition function. The nearly equality is a remnants of the fact that we have taken the classical limit here, and this is nothing but summation of some kind of a Boltzmann factor to the power of n divided by n factorial. So, can I call this as nothing but a single partition function raised to the power n divided by n factorial. So, this is like already the birth of the Boltzmann statistics. So, Z1 is a single particle Boltzmann partition function. See, it is like you compute partition function for a single particle and raise it to n power, that will give you v to the power n and 2 pi m over beta to the power 3 n and so on and so forth, and this 1 upon n factorial is the factor that comes due to the indistinguishability of n particles, which you have to artificially plug in classical statistical mechanics to avoid Gibbs paradox. Here you do not have to do anything. Okay. So, this n factorial was embedded in the wave function of the fermions and the bosons, and when you take the high temperature limit you get the correct statistics which requires no artificial plugging to save you from an entropy crisis. So, this is a single particle partition function. Let me complete my statement. and this n factorial here is because we got indistinguishability. What do you mean by indistinguishability? Particles are identical. So, if I permute with n particles, I have n factorial permutations, each one of them will have exactly the same Hamiltonian and the wave function does not change, which means I must not overcount my microstates. So, this is precisely the factor by which you would overcount your microstates and get incorrect entropy. Well, that is naturally avoided in quantum statistics, because you do it in the grand canonical ensemble and you take into account the proper symmetrization and anti-symmetrization of the wave function, and so this n factorial is already embedded in your calculation. Anyway, it is relieving and it is eye pleasing to see that everything falls intact when you take the high temperature low density limit of the quantum partition function. We are not there fully yet, because we must determine Z1, or if we determine Z1 we will end up determining Z, because Z1 to the power n by n factorial is your Z. So, that is the only agenda remaining. Okay. So, let us complete this discussion, and to do that all I have to do now is to basically go from discrete states to integration over a continuum of states. So, if you look at the Boltzmann partition function, this Z1, this is nothing but a partition function that is written in for discrete degrees of freedom. So, we can go from discrete states to a continuum of states. I will call this as a thermodynamic limit. As the number of states become squeezed so tightly that the separation between the states disappears. So, you do not work with summation anymore. What you would work now with is the density of states. So, the summation must be replaced by density of states. That is the logical thing to do when you have a continuum of states. Okay. And since we are taking a thermodynamic limit, volume being very large, we must work with an integral representation. Okay. If you recall the partition function for an ideal gas, you did not use a summation over all states, because an ideal gas Hamiltonian is continuously is a continuous function. Particles can go in any corner of the box with any momenta. Since position and momentum are continuous random variables, you would expect the Hamiltonian to be also continuously varying. So, you had the integral version of the partition function. So, I can compute this g of k, as we have been doing all along. This is nothing but you can write down this as d cube k over pi by L the whole cube, and keep in mind that you have to take 1/8 of the total volume, because you do not take negative excitation numbers, avoid negative quantum numbers. And just to remind you why we do not take negative quantum numbers, because taking a negative quantum number does nothing spectacular to the system except apart from giving the wave function an overall negative sign. And since wave function itself is nothing, it is just the probability amplitude, what is really meaningful is the probability density, which is the wave function multiplied to its complex conjugate. and in that process a negative or a positive wave function gives you the same probability density. So, we work with only 1/8 or 1 octant of the case space, and to respect that observation we have taken a factor of 1/8 here. Okay. So, now we can take this g of k and compute our partition function, the last and final step. So, this is my left hand side, and the right hand side is nothing but I have 1 upon factorial n already with me, and that integral over the Boltzmann factors to the power n has now to be replaced with I can write down this entire thing as an integral, okay, over I can write down this as let me just write down these prefactors outside. So, this becomes L cube in the numerator becomes just volume divided by pi cube, okay, and I am going to write down 8 here, V upon 8 pi cube, and I have a triple integral, okay. So, this is like kx, ky and kz going from minus infinity to plus infinity, okay, e to the power minus beta, and energy is nothing but h cut square k square over 2m, okay, and this is nothing but integrated over the volume element, okay. Please look at here if to refresh your memory. Okay. So, this summation j over the Boltzmann factor is now my integral, and the entire thing is raised to the power n, which is basically this power, and there is a 1 upon factorial n outside, okay. And just to remind ourselves, we have taken the liberty to replace energy of the jth state as h cut square kj square over 2m, okay. So, my Boltzmann factor is now e to the power minus beta h cut square k square upon 2m. Now, you can see that these are nothing but 3 independent Gaussian integrals. I can write down one more step here. So, I am going to write down this as 2 pi the whole cube, 8 pi cube, and the triple integral kx, ky and kz all going from minus infinity to plus infinity, e to the power minus beta h cut square over 2m into kx square plus ky square plus kz square since the integration variable is dummy, there is nothing but a single integral to the power 3, okay. So, I am going to write this as v to the power n over 2 pi to the power 3 n. A single Gaussian integral is square root of pi by a. So, I am going to write pi over a is nothing but beta h cut square into 2m. This will give me a factor of 3, so power of 3, because there are 3 integrals here, and overall it will also be raised to an n because there is a big n sitting outside. Of course, it is square root, so 3 n by 2, fine. Okay. Little bit of recap. So, minus infinity to plus infinity e raised to minus ax square dx is equal to square root of pi over a. Okay. I have a product of 3 of them. So, I will call this as pi by a to the power 3 half, and if I have 3 n, I will say that this is entire thing is nothing but 3 n by 2. That is all. Let us rearrange the terms so that it becomes familiar to our eyes. So, I am going to take 2 pi raised to 3 n inside this bracket, which means I have to raise it to the power 2. So, I am going to write down 2 pi m in the numerator as it is and take this this guy inside. So, this should become 2 pi to the power 2 because there is a half also outside into beta h cut square raised to 3 n by 2. Okay. There is a square root sign, so I had to raise it to the power of 2. It was already raised to 3 n, so that does not get affected. So, this becomes now I can knock off a few things. So, h cut is nothing but h upon 2 pi. So, 2 pi square h cut square is nothing but just h square. Okay. So, this is nothing but 2 pi m over beta h to the power 3 n by 2 square, and let us take this h square also outside. So, what I get is 1 upon n factorial into 1 upon h to the power 3 n into 2 pi m over beta to the power 3 n by 2. This is my canonical partition function for an ideal gas, classical ideal gas. Did I miss something? Yeah, v to the power n. What we started was for the system of fermions and bosons at low temperature. So, we started from Fermi-Dirac statistics and we systematically took the high temperature low density limit in the limit of large volume, and what we ended up getting is statistics where it does not care whether you are looking at bosons or fermions, particles are behaving ideally, they are point size particles and everything is neat and intact. This tells you that no matter whether you start from Bose-Einstein statistics or Fermi-Dirac statistics, the high temperature low density limit will take you to the ideal gas behavior, which is a beautiful correspondence that I do not see any difference between the Fermi-Dirac statistics or Bose-Einstein statistics. They both behave like a ideal gas of non-interacting particles. So, I know for sure that this partition function is related to the thermodynamic free energy as e to the power minus beta f, and so this partition function will give me the correct values of the equation of state, the pressure, the entropy without any problems that we encountered in classical statistical mechanics, where we could not take the n factorial without an ad hoc substitution. So, here the expression that you get by this systematic process is the correct expression, where the n factorial is a natural factor of indistinguishability. It did not have to be artificially plugged in. This factor h is Planck's constant. Again, I did not have to take a Planck's constant and plug it artificially like I did in the classical stat mech, because I had to non-dimensionalize the partition function and attribute some kind of a cell factor the resolution of my phase space, it had the dimensions of action. Here H is the Planck's constant that came from the Bose-Einstein or Fermi derived statistics. So, the remnant H is the Planck's constant. So, we must call this H as Planck's constant because it came from quantum mechanics. Okay. You do not get Planck's constant in classical mechanics because Boltzmann and Gibbs would not have known this Planck's constant because this was done only in the dawn of 20th century when quantum mechanics was actually developed, whereas classical stat mech predates quantum mechanics, it was done before quantum mechanics was developed. So, the H that is there in the Boltzmann and Gibbsian stat mech is not Planck's constant, at least they did not know. They used a cell factor, they used a non-dimensionalizing factor, something that has dimensions of angular momentum or action. Now we know that this H is the Planck's constant because we started from the quantum statistics and systematically derived classical statistical mechanics, which gives us the correct enumeration of states. There is a factorial n sitting here which avoids overcounting microstates and gives us the correct expression of entropy, and so is the expression dimensionless because of the H factor sitting in the expression. So, I will conclude this discussion of the quantum to classical correspondence. When we meet again, we will discuss some working examples, and that is the end of the course. So, we will stop it here.